it's a negative charge, the flux would have to be pointing inward, right? This electric field for a negative charge points to the negative charge. Positive charges, the field branches out. You know, the universe doesn't care about that, right? The idea that we give the field a direction is actually us. The universe just communicates. Okay. Oh yeah, there we go. The Geiger counter. This is a practical application. And this looks like a really nasty problem, doesn't it? It really isn't. So, it says here, the figure shows a Geiger counter, a device used to detect ionizing radiation, which causes ionization of atoms. A thin, positively charged central wire is surrounded by a concentric, circular, conducting cylindrical shell with an equal negative charge, creating a strong radial electric field. The shell contains a low pressure inert gas. A particle of radiation entering the device through the shell wall ionizes a few of the gas atoms. What is ionization? What's ionization? Yes, sir.
You know, like charging up the molecules.
Charging up the molecules?
Yeah.
Losing a
Like
valence
polarizing.
electron?
Well, not molecules.
Losing a valence electron?
Yeah. Yes, atoms. You're talking. I want to get him into the context of atoms. It's basically you're losing electrons or gaining electrons to an atom. And so, because an atom, a regular atom is electrically neutral. It basically has a negative and a positive nucleus and a negative electron cloud around it. And so they'll be electrically neutral, but you can lose electrons. You have donor electrons in the outer valences.
Yeah.
And so you can lose them, and so then it becomes positively charged. Or you could have, there are certain atoms where there are certain valences that are unoccupied, and they can gain electrons and become negatively charged. So, and then in each case, those are ions. And those ions themselves can be transported back and forth. And so what happens here is that you're getting this radiation that comes in, and it's able to ionize the atoms in the gas that can be detected. So that's what we're looking at here. Particle of radiation entering the device through the shell wall ionizes a few of the gas atoms. The resulting free electrons are drawn to the positive wire. However, the electric field is so intense that between collisions with gas atoms, the free electrons gain energy sufficient to ionize these atoms also. More free electrons are thereby created, and the process is repeated until the electrons reach the wire. The resulting avalanche, okay, and that's exactly how that's that word that we describe the process. It's like they show the avalanche right there. They reach the wire. The resulting avalanche of electrons is collected by the wire, generating a signal that is used to record the passage of the original particle of radiation. Suppose that the radius of the central wire is 25 micrometers, the inner radius of the shell is 1.4 centimeters, and the length of the shell is 16 centimeters. If the electric field at the shell's inner wall is 2.9 times 10 to the 4 newtons per coulomb, what is the total positive charge on the central wire? And when you think about it, all of that verbiage on there is just basically background. Okay, what it really wants is, what is the total positive charge on the central wire of something that's at the center of a cylinder? Yeah.
Will the test questions be this worded?
No. No, goodness no. This is why this is just a homework question. I want you to especially over the weekend. Gotta have something to do on the weekend, right? So, ooh, what do you think of that sketch? It's a little better, yeah. 15 minutes. I was feeling artistic. So our signal is coming in through the wire. We have the wire, the radius of the wire is 25 micrometers. The radius of the entire cylinder is 1.4 centimeters, inner radius. The length is 16 centimeters. The electric field, the inner electric field is 2.9. That's basically 2.9 times 10 to the 4. That's what, 29,000? 29,000 newtons per coulomb. That's a pretty strong field, isn't it? Yeah. So we want to find the charge on the wire. So in this case here, what we want to do is define a Gaussian to coincide with the inner wall of the cylinder. We're going to test the field at that location on the inner wall. So we set up Gauss's law as E dot dA is Q enclosed over epsilon naught. And we just then, in this case here, all we have to do is make Q enclosed equal to the Q. Okay? So simplify everything down to our, we're all using cylindrical symmetry. So the cosine is not, the cosine is 1. Cosine of 0 is 1 everywhere in the problem, so you don't need that. And so we're just, E is constant because the charge is constant. And we end up with just the surface area of our cylinder, which is 2 pi r times L. And so then we solve for Q, which is basically to multiply our entire flux by epsilon naught, which is what we did before. And we have all the numbers, and so we end up with a value of 3.6 nanocoulombs. Yes, sir?
So, why are we doing the area of the cylinder, the DA? Why is that the cylinder?
Because that's where we are testing. You said we want to define our Gaussian to coincide with the inner wall of the cylinder.
Right.
So we're using Gauss's law to determine the charge on the central wire. And so what we're doing is we're actually identifying the field at a known distance, and then getting that field, and because we know that value, we just reverse engineer it to find the charge.
Well, the field is coming from the positive wire.
That's right. And it's branching out in all directions. It's going to the right, to the left, out, in, and so on. And so we know its strength right at the inner wall. Does that make sense?
Yeah, I'm just confused why the field is coming from the wire, but we're using the area of
Well,
the
it's,
cylinder.
we're testing the field at that distance because we know its value. See,
Oh,
what,
okay, so it's just a
yeah.
perimeter.
See, what we want is to solve for the charge, and what we need is an equation. We need an equation that lets us calculate the charge based on known values. And when you have an equation, you have, if you don't have an equation, you can't solve for anything. You have to have something on the left-hand side and something on the right-hand side. And so we have the ability to calculate the electric flux of, at the inner wall. And so, and we know that there's a constant epsilon naught on the right-hand side. So the charge actually could be calculated pretty easily if we have certain values.
So the Gaussian cylinder that you drew on the inside is all the way to the outside, all the way to basically the inner wall of the.
The field is branching all the way out. And what we're testing it actually is right there.